Okay, in this lesson, we're going to talk a little bit more about eccentricity, and we're going to combine this with the fact that these conic sections that we've been discussing can also be written in a polar form. So in general, any conic can be defined as the locus of points such that the distance from any point P on the conic to the focus and the distance from a fixed line not containing P is a constant ratio. So if you remember that we actually defined parabolas in a very similar way. Parabolas was the set of all points. If you take any point on this parabola, the distance from the focus to that point and the distance from the that point to the directrix is the exact same value. So what we're going to do here is we're going to define every one of our conics based on a focus and a directrix instead of two foci or whatever else. So D1 in each of these, D1 is going to be the distance from the focus to the point on the conic. D2 is going to be the distance from the point on the conic to the directrix. Therefore, the constant ratio that I'm talking about, this constant ratio is actually the eccentricity of the conic. So therefore, eccentricity, or E, is going to be the ratio of D1 to D2. And if you remember correctly, the eccentricity of a parabola was 1. The reason why? Because D1 and D2 was the same distance. However, let's look at our other conics and the eccentricity of each. So if you're dealing with an ellipse, again, eccentricity is D1 over D2. Take the focus, and then notice that we've defined a directrix here. The D1 value, notice that D1 is going to be smaller than D2 when we're dealing with with an ellipse. And that's even if you pick any point. If you pick this point right here, here's D1 and here's D2. D2 is a little bit longer. No matter what point you pick, that D1 over D2 is going to be a constant, same thing every time. So therefore, when you're dealing with an ellipse, since D1 is greater than D2, then your eccentricity is going to be less than 1, but it's going to be greater than 0. It'll always be somewhere between 0 and 1 because, again, D1 over D2 will be a fraction. Okay, when you're dealing with a hyperbola, notice again, here's our focus, and here's our defined directrix. D1 is actually larger than D2. So when you're dealing with a hyperbola, your eccentricity will always be greater than 1. And then finally, we're back to the parabola where D1 and D2 are actually the exact same. That's the definition of a parabola. So your eccentricity of a parabola will always be equal to 1. Okay, now let's look at the polar form of these conic sections or conic equations. The equation of a conic with eccentricity E. The focus located at the pole, so we're going to put our focus on every one of these. It's going to be located at 0, 0. It's going to be located at r equals 0 and theta equals 0 at that pole. And the vertical and horizontal directrix can be written in the following polar forms based on the location of the directrix relative to that pole. If we do a directrix here at x equals negative k, which would be to the left of the pole, then this would be our equation of the conic. If it's to the right of the pole over here at x equals k, then this is going to be the equation. So all depending on where we place our directrix, we're going to have these different equations. Below the pole is here, and that would be a y equals equation, and then above the pole would be here. So that's all the different ones based on where we let that directrix be. And that might not make any sense right now, so let's go ahead and look at some of these. Number one, let's identify the eccentricity, the type of conic, and the equation of the directrix for each polar equation. So each of these equations represents all of your different conics based on whatever that E value is. So let's first off match up. R is equal to 6 over 1 plus 2 sine theta, and that would match up with this right here. So now let's figure out what our eccentricity is. So let's go ahead, since it says, let's see, well, we don't have to put this, but I'm going to. I want to list that would be above the pole. Our eccentricity can be found right here in front of the sine, so that's going to be an eccentricity of 2. So that tells us what type of conic we have. An eccentricity of 2 would be a hyperbola. And then finally, where is our directrix? Okay, going back to this, the directrix would be above the pole, and we've got to find this value of k right here to figure out what that is. Okay, on top of our equation, we have k times our eccentricity. We have the number 6. Since our eccentricity was 2, that means our k value would have to be 3. So therefore, my directrix is going to be located at y equals 3. So that's it. That's going to be a hyperbola with a directrix at y equals 3 and an eccentricity of 2. The next one, number 2, let's match it up with one of these. We have 1 minus something times cosine theta, which is obviously going to be this one. So that's going to be to the left of the pole, would be our directrix. The eccentricity, again, is the number in front of cosine, so 0.3 is our eccentricity. Since our eccentricity is below 1, it's between 0 and 1, that means that our conic is an ellipse. The directrix we can find by looking at the top. The top, notice again, is the value of k times e. So this is going to be k times 0.3. So that means my directrix must be at 5. But it's going to have an equation of x equals, now notice it says x equals negative k. So that's going to be x equals negative 5 would be my directrix. Number 3, we have 7 over 1 plus cosine theta. Let's again match it. 7 over 1 plus cosine theta would be right here. Look at the number in front of cosine theta to find your eccentricity, and that'd be an eccentricity of 1. The only conic that has an eccentricity of 1 would be a parabola. So therefore, here you have a parabola. On top, you can find your k value. Again, on top is k times the eccentricity, so that means that my k value has to be 7, and I didn't put on that where the pole was located, or excuse me, where the directrix. That's going to be right of pole. And since now, hopefully you're getting the hang of this, since my directrix is to the right of the pole, it's going to be over here. And this k value pretty much tells you how far it is over to that directrix if you haven't figured that out. So since our k value is the distance of 7 over to my directrix is going to be located at x equals 7. Number 4. Let's first figure out which location we have. So we have 1 minus 0.8 sine theta on bottom. The only one that's 1 minus stuff times sine of theta is right here. My eccentricity, and that's going to be below the pole. Below the pole. Again, my eccentricity is going to be 0.8, which means I have an ellipse. Since you can look at the top to figure out what your k value is. Again, the top is going to be k times your eccentricity, so therefore that means my k value has to be 1. And since that directrix is going to be located below the pole and it's going to have a k value of 1, that distance right here is 1, that's going to be y equals negative 1 is going to be my directrix. Okay, number 5. Now let's read our note here. It says, note, you must write the equations in standard form by factoring and simplifying. So we've got to make this look like our standard form at the top. And if we go back and look at those standard forms, I want to point out that it's always 1 plus or 1 minus e times sine of theta. So we're going to have to clean this up some. So let's do this. Let's factor the 2 out of the bottom. So that's going to be 10 over 2 times 1 minus sine theta. And then we can cross cancel that 10 and that 2, and that gives you a 5 over 1 minus sine theta. So now we can match it. 1 minus sine theta is going to be that exact same one. Our eccentricity, obviously, is going to be the number in front of that sign. So we're going to have an eccentricity of 1 here. So it has to be a parabola. 1 minus sine theta, again, let's go back. That means that my directrix is going to be below the pole. So let's go ahead and write that, below the pole. So on top, we can find our k value. This is going to be k times e, and since our eccentricity is 1, that means we have a k value of 5. And let's go ahead and sketch that out. Here's the pole. My directrix is going to be located 5 units below that pole with a k because of the k value of 5. So therefore, my directrix is going to be at y equals -5. Now, if you want a way to remember where the pole is or where the directrix is located, let me give you a tip here. Remember that cosine values corresponded with x values. X values are left and right values. If it's a minus cosine, notice it's to the left. If it's a plus cosine, notice it's to the right. Again, sine values correspond with y values. If it's a minus sign, notice it's below, and if it's a plus sign, notice it's above. So that's a good way of remembering these. So therefore, let's see if we can do that on our next one without having to look back. So number 6, we are going to have to factor the bottom out. So let's pull an 8 out of the bottom. So you have 16 over 8 times. And you might be saying, well, you can't pull an 8 out of the 12, and you're going to have to. You're going to have a decimal or a fraction there, but you are going to have to factor that out because you have to have a 1 here. So it's going to be 1 minus. And what do you multiply 8 by to give you 12? Well, if you multiply it by 12 eighths, the eighths was cancels, and that would give you that 12. So you could write it as 12 eighths if you wanted to. Cancel the 16 and the 8, and that gives you a 2 on top. So you have 2 over, that's going to be 1 minus 12 eighths. You can reduce that to 3 halves cosine theta. And again, notice the cosine. So that means that your directrix is going to be left or right of the pole because it's an x value. Since it's a minus, that means your directrix is going to be over here to the left of the pole. So I'm just going to put left right there, left of the pole. Let's go ahead now and find your eccentricity. The eccentricity is always the number in front of that sine or cosine. So you have an eccentricity of 3 halves here, which means you have a hyperbola. Next thing is let's find our k value. The top is always k times the eccentricity. So you got to figure out, okay, since our eccentricity is 3 halves times what k value is going to give you that 2. To figure that out, flip and multiply the other side by 2/3, and you're going to get a k value of 4/3. So the distance from here over to here is 4/3. So therefore, you're going to have a directrix at x equals -4/3. Okay, number 7. Again, you have a -4 on bottom. That's going to have to be factored out. So let's write this as -12 over -4 parentheses. 1 plus, first off, because a negative times a positive will give you this negative. But what can we multiply -4 by to give us a 1? And that would be a positive 1/4 because the 4s would cancel. So you have 1/4 cosine theta. The -12 and -4 would cancel and gives you a 3 on top and a 1 plus 1/4 cosine theta on bottom. Since you have a cosine value, that's going to be a directrix either to the right or left. Since it's a positive cosine, that means that your directrix will be located to the right of the pole. So I'm going to put right of pole. Your eccentricity is always in front of that cosine, so you have a 1/4 for an eccentricity, which means you have an ellipse because it's between 0 and 1. The next thing is let's find our value of k. This is k times the eccentricity. So k times 1/4 is equal to the 3 on top. Divide both sides by 1/4 and you get a k value of 12. So therefore we're 12 units to the right of the pole. So that's going to be a directrix of x equals 12. Okay, number 8. Let's factor out the 5 on bottom. So you have a 45 on top. 5 parentheses, 1 plus, again, if you multiply 5 times 6/5, the 5s would cancel, so 6/5 sine theta. 5 and 45 reduces to a 9, so you have 9 on top, and 1 plus 6/5 sine theta on bottom. So therefore, you have an eccentricity of 6/5. Since that's greater than 1, this will be a hyperbola. Let's figure out where the directrix is going to be. Since it's a positive sign, again, sign values are y values. So that's going to be above, since it's a positive sign. So I'm going to put above there. Your directrix is above the pole. On top, this value is the k times e. Since the eccentricity is 6/5, then 6/5 times k is equal to 9. To get rid of that 6/5, multiply the other side by 5/6. Cross cancel, that'd be a 3 and a 2, which gives you a k value of 15/2 or 7.5. Therefore, your directrix is located 7.5 or 15/2 units above. That's going to be a y equals equation. So y equals 15/2 or y equals 7.5. Number 9. Again, factor the 3 out of the bottom gives you negative 18 over 3 times sine of theta. Now we got a problem here though. We need a 1 plus or 1 minus. We don't need sine of theta minus 3. So what I'm going to do instead, so I can flip-flop these two, is I've got to factor out a negative 3. Then that turns this into a positive 1, and it turns this into a minus sine theta. It flips them. Reminder, that anytime you factor out a negative, it flips your two terms together, or it flips your two terms. Reduce this, that to be a 6 and a 1. So you have 6 over 1 minus sine theta, which means your pole is going to be, since it's a 1 minus sign, that means it's below the y. So therefore, that's where it's going to be located, below the pole. Your eccentricity is in front of the sign, so you have here an eccentricity of 1, which means you have a parabola. Your directrix is located k units away from your pole. So we know that the top again is k times the eccentricity. So therefore, your eccentricity, which is 1 times your k value, is equal to 6. That means your k is 6. So therefore, we're 6 units down right here. So therefore, y equals negative 6 would be my direction. And number 10. Again, we're going to factor the 4 out of the bottom to give us what we need. So that's going to be 1 over 4 parentheses, and that'd be 1 minus 0.4 cosine theta. Nothing really reduces there. However, I have to have this to be a 1 right here. So how are we going to do this? One method of doing so is I could take and multiply top and bottom by 1/4, which is legal because I'm doing it to both. So therefore, my equation is now going to be r equals, there's going to be a 1/4 on top, and then these cancel and leaves me with a 1 minus 0.4 cosine theta on bottom. Okay, negative cosine, that means cosine is going to be an x value. Negative is to the left. So my directrix is going to be to the left on this one, the left of my pole. The number in front of cosine is my eccentricity, which is 0.4, which means you have an ellipse. My directrix is k units away from the pole, so therefore this, again, is going to be k times my eccentricity. So that's going to be 0.25, which is the top, is equal to 0.4 times k. When you divide by 0.4, you're going to get a k value of, well, instead of using a calculator, let's just do this. Multiply top and bottom by 100, and that moves your decimals over twice. That's going to be 25/40ths, and then just reduce it. That's going to be a k value of 5/8. So therefore, my directrix is located at x equals negative 5/8, since it's 5/8 units to the left. Okay, starting with number 11, it says determine the type of conic given by each polar equation, then we're going to graph it. To determine the type of conic, all we have to do is look right here at the eccentricity. Since the eccentricity here is between 0 and 1, this should be an ellipse. Ellipse, there we go. And the way we're going to graph it is we'll just use a table of values here. So here's my table of values, and again, I'm just simply plugging in cosine of 30. We'll do a couple of them for you. That's going to be root 3 over 2, multiply by 0.5 and add 1. And you get somewhere around 1.43. When you do 3 divided by that answer, you get right at 2.09. We'll call it 2.1. And we're just going to do the exact same thing for each of these values. 3 divided by, and you can type the whole thing in, 3 divided by 1 plus 0.5 times the cosine of 60, 3 divided by 1 plus 0.5 times the cosine of 90, and so on and so forth. And here's the values that you get. And let's go ahead and plot those. So at 30 degrees, you have a radius of 2.1. So go up to 30 degrees, and there's a radius of about 2.1. 60 degrees would be 2.4, so somewhere right around in there. I should have put 0 degrees in as well, but we can go back and do that in just a second. At 90 degrees, I get a radius of 3. At 120 degrees, I get a radius of 4. So that's going to be right in there. At 150 degrees, I get a radius of 5.3. So that's 4. Let's see, 5.3 is going to be right in there somewhere. Then at 180 degrees, I get a radius of 6. And you could, again, that's going to be half of it. Now we need to continue on. And once you continue on and plug in 210 and plug in 240 and 270 and so on and so forth, here's what your graph is going to look like. And then once I do connect my dots, here's my finished graph. And we do see that we have a perfect ellipse there. Now, something I didn't cover that I want to go back and hopefully makes more sense to you. If you were to find the pole, since it's 1 plus cosine, you have a pole located to the right, or excuse me, a directrix located to the right of the pole. And if you did the math here, that directrix would be located at x equals 6, which is right there. So now what we've got going on is this 0.5 is a ratio. The ratio of D1 to D2 is going to be 0.5 or a 1 to 2 ratio. Now, what does that mean? That means for every point, and I've done it for a point right here, every point on this ellipse, the ratio of D1, which is the distance to the focus, to D2 is a constant 1/2. So if you were to take this distance right here to this distance right here, it would be a 1 to 2 ratio. Or pretty much this distance is double D1. And that's true for every point on this ellipse. Okay, the next one. Our pole is located negative sign. Our pole is located here below our directrix is located below the pole. Our eccentricity here is equal to 1. So therefore, this should be a parabola. And again, I'm not going to do a table of values. What I'm going to do is I'm going to type straight into my calculator, 0 degrees. I'm going to do 2 divided by 1 minus the sine of 0. The sine of 0 is 0. 2 over 1 minus 0 is 2 over 1, which is 2. So at 0 degrees, I have a radius of 2. And I'm just going to do that for each of my angle values. And when I do, here's the graph I get. And I've just done a few points there, and you can see the parabolic shape. That is a parabola. That's a poorly drawn parabola there. The next one, we do need to factor the 4 out of the bottom. So we have 36 over 4 parentheses 1 plus 3 sine theta. The 4 and 36 reduces, and there's what we have. So therefore, we have an eccentricity of 3. So this should be a hyperbola. Once you plug in some values and graph, here's what it should look like. Okay, here's the points I've plugged in from 0 degrees up to 180 degrees. Now, I want to show you a kind of a trick that you can actually use Desmos to plug in some of these values if you want to, so that you're not having to plug in so many values into your calculator. Okay, so here's Desmos, and notice what I've done. I've typed in my equation as y equals and x equals, and the reason I did this is because if you're just wanting to Desmos to plug some values in for you, it won't do it as r's and thetas for some reason. So I typed it in as x's and y's, and then you can do a couple of different things here. You can click on this and click the settings button right here, and notice you can duplicate it with this button. Or right next to it, it has a picture of a table. If you click on the table, it actually creates a table for you. Make sure that if you want to type in degrees, that you're in degree mode. If you want to type in radians, that you're in radian modes, and that can be changed here and here. So I want to type it in as a degrees, and then you can just click on the different x values here, and you can simply delete what they have and type in maybe 0 degrees. If you hit enter, you can type in even like 15 degrees, 30 degrees, because I noticed on our graph it goes up by 15 degrees each time. There's 60, 75 degrees, 90 degrees, and it will actually plug in those values for you. And it gives you your R values over here on the right side. So when you're at 0 degrees, your R value is 9. You're at 15 degrees, your R value is 5.1, and so on and so forth. So there's all the angle measures from 0 to 180. Now let's plug in a few more. And there's the other half of your hyperbola. Okay, number 14. First off, let's factor the 2 out of the bottom. Gives you negative 10 over, and we got a problem again. The cosine is listed first, so we're actually going to have to factor a negative 2 out so we can flip-flop those. So factoring out a negative switches these, and then you'll have a 1 minus cosine theta. Negative 2 and negative 10 cancels, leaves you with 5. So 5 over 1 minus cosine theta. So therefore, you have an eccentricity of 1. So therefore, this should be a parabola. So let's see what this parabola looks like. Again, doing the exact same thing. You can either just use your calculator to plug values in, or you can use Desmos and use the table there. But once you do it, either way, regardless, this is what your graph will look like. And there it is.